Welcome to this first video of my playlist about the preparation of aryl amines. These are important target compounds and intermediates for a wide range of products. In this video we'll have a look at the reduction of nitroarenes. This is the most relevant strategy for the preparation of anilines. Therefore, I've also included at the end of this playlist a video about the preparation of nitroarenes by electrophilic nitration. In part 2, I show you examples of the preparation of aryl amines by uncatalyzed aromatic nucleophilic substitution. These include acid and base catalysis, but not transition metal catalysis, which is discussed in part 3. In part 4, we'll have a look at the oxidative C-C bond cleavage of benzoic acids, aryl ketones, and related compounds, for instance the Curtius rearrangement. Part 5 is about the direct electrophilic amination of arenes by substitution of hydrogen. In none of the videos I've considered photochemical or electrochemical transformations because their scope and predictability is limited, special equipment is required, and upscaling such reactions is difficult. Most aromatic nitro groups are easy to reduce to anilines. As intermediates, a nitrosoarene and a hydroxylamine are formed, which are more reactive than the starting nitroarene and can yield a number of byproducts. Under acidic conditions, the intermediate hydroxylamines, for instance, can isomerize to phenols or react with nucleophiles at positions 2 or 4. These hydroxylamines are also strong nucleophiles and can yield azoxy compounds by condensation with the nitroso intermediate. Reduction of azoxybenzene can then yield azobenzene or diphenylhydrazine. The intermediate hydroxylamine can also react irreversibly with ketones, esters, and nitriles, and these compounds should better not be chosen as solvents. Aniline is an important intermediate, and each year around 7 million tons are produced worldwide. Aniline is a weak base, around 6 orders of magnitude weaker than ammonia or aliphatic amines. Its acidity is much higher, and alkali metals and even magnesium and aluminum readily dissolve in hot aniline, yielding hydrogen and the corresponding anilide salts. Unfortunately, aniline itself and a number of substituted anilines can cause cancer and should thus be handled with care. Aniline often contains oligomers formed by oxidation, such as benzidine, which are even stronger mutagens than aniline. On an industrial scale, aniline is mainly prepared by hydrogenation of nitrobenzene, and to a lesser extent by nucleophilic amination of chlorobenzene or phenol. As hydrogenation catalysts, supported copper, nickel, or palladium are often used, and the high reaction temperatures provide for a long catalyst life. The hydrogenation is highly exothermic, what can be a problem in large-scale laboratory preparations. Most aniline is converted to methylene diphenyl diisocyanate, an important monomer for the manufacture of polyurethanes by reaction with diols. Further products include the antioxidants phenylene diamine and diphenylamine, as well as cyclohexylamines, quinoline, benzoquinone, and mercaptobenzothiazole. The latter is used in the vulcanization of rubber. I'll show you now some specific examples of the reduction of nitroarenes to anilines. Hydrogenation is often the most inexpensive and environmentally friendly method. Even in the presence of other groups that may be hydrogenated, nitro groups often react first, as in this example. To avoid over-reduction, a catalyst of low reactivity or a low reaction temperature may be helpful. Ideally, the hydrogenation should be stopped as soon as the theoretical amount of hydrogen has been consumed. Selective reductions can also be achieved with some metals, for instance with magnesium or aluminum in methanol, as shown here. With alkali metals, however, product mixtures are often obtained. There are 2 older references about the reaction of nitroarenes with alkali metals in the description of this video. Zinc in the presence of acids is another convenient reducing agent for nitroarenes. In this example, a vinyl group remained unchanged during a reduction with zinc. Here the starting nitroarene also contained an alkyne and a sensitive carbon-iodine bond. Still, treatment with an excess of zinc in acetic acid gave a substantial yield of the aniline. The classical reagent for reducing nitroarenes is iron in acetic acid. As shown here, this metal also enables highly selective reductions, which would be difficult to achieve by catalytic hydrogenation. This is an example of selective rhodium-catalyzed hydrogenation of a nitroarene. The hydrogen was generated from hydrazine, and again the nitro group was reduced much faster than an olefin or a carbon-bromine bond. Also tin dichloride can be used to reduce nitro groups. Here such a reduction succeeded in the presence of an electron-deficient alkyne and an ester. Electron-deficient nitroarenes, for instance metadinitrobenzene, can be selectively monoreduced with sulfide. Reducing nitroarenes in the presence of aldehydes, ketones or nitriles can yield alkylated anilines. The main reason is the high nucleophilicity of the intermediate hydroxylamines. Here, for instance, a high yield of an isopropyl aniline resulted upon reduction of 4-methoxynitrobenzene with zinc in the presence of a slight excess of acetone. Even simple aliphatic nitriles can react with nitro groups during reductions. In this example, catalytic transfer hydrogenation at room temperature and in the presence of an excess of hexyl cyanide gave a good yield of heptyl aniline. Instead of stoichiometric amounts of iron, nitro groups can also be reduced with catalytic iron salts and an excess of a reducing agent, triethylammonium formate in this case. When such a reduction was conducted in DMSO, however, dimethylanilines resulted. The required formaldehyde probably originated from DMSO, as shown here. DMSO is a rather unstable solvent and can lead to many unexpected byproducts. It is even possible to prepare cyclohexylanilines by hydrogenating mixtures of nitroarenes and phenols. This will only give high yields when the phenol is hydrogenated to cyclohexanone faster than the aniline to cyclohexylamine. In this example, the intermediate aniline was probably stabilized by conjugation with the methoxycarbonyl group. Here, cyclohexane carbaldehyde was generated by rhodium-catalyzed hydroformylation of cyclohexene. One-pot hydrogenation with nitrobenzene gave a good yield of alkylated aniline. The same aldehyde as in the previous example can also be generated by catalyzed dehydrogenation of a primary alcohol. The resulting hydrogen was sufficient to bring about reductive alkylation of nitrotoluene. At high temperature, nitroarenes react with phosphides to yield nitrines and other reactive intermediates. In the presence of aryl boronic acids, these can undergo arylation, as shown here. Unfortunately, boronic acids are too expensive to make this approach economically viable for most potential target products. I've sketched here one possible mechanism of this reductive arylation, that at 180 degrees Celsius homolytic bond cleavage and nitrines may also have been involved. Let's have a look at some potential side reactions. Under carefully controlled conditions, it is possible to stop the reduction of nitro groups at the hydroxylamine stage, as in this example. N-aryl hydroxylamines are mutagenic intermediates that readily react with ketones, esters and nitriles, as shown on previous slides. Aryl hydroxylamines can also be isomerized to aminophenols by treatment with acids, the so-called Bamberger rearrangement. One convenient preparation of paracetamol from nitrobenzene is in fact based on this isomerization. Here, a mixture of aluminum and oxalic acid was used to bring about both the partial reduction and rearrangement of 2-fluoronitrobenzene. If a lot of some other nucleophile is present, intermediate hydroxylamines may not yield 2 or 4 aminophenols, but other substituted anilines instead. In this example, chloride added at position 2 of the hydroxylamine and 2-chloroaniline resulted. One side reaction of the catalytic hydrogenation of nitroarenes is hydrogenation of the arene. This can cause the formation of cyclohexylamines, cyclohexylanilines, cyclohexanones, or cyclohexanone oximes, as in this example. Here, hydroxylamine hydrochloride had been added, but a nitrosyl cyclohexane intermediate could also tautomerize to cyclohexanone oxime. Nitroarenes may also undergo nucleophilic substitution of nitrite, especially if other electron-withdrawing groups are present, as in this example. This could become a problem when strong nucleophiles are used as reducing agents, such as hydrazine, sulfide, or thiols. The reduction of nitroarenes with phosphorus-3 derivatives can cause the formation of nitrines. In this example, despite the relatively low reaction temperature, a nitrine and then a substituted azepine were formed. Here's a selection of some further examples of nitro group reductions, which you can also find in the description of this video. The next video of this playlist is about the preparation of aryl amines by uncatalyzed nucleophilic substitution. Although in recent years research has focused on transition metal catalyzed substitutions, such catalysts are often unnecessary, and many examples of successful uncatalyzed nucleophilic aminations have been reported. See you then!